Hi everyone, welcome to enginerdmath. In this video, I will teach you about delta and Y connected resistors. Okay, so far we have discussed about different types of connections for resistors, like series connections, parallel connections, and even combination series to parallel connections of resistors, right? But what if we encounter a type of connection that cannot be simplified or that cannot be described as a series, parallel, or series to parallel connection of resistors? So probably this type of connections can be delta and Y connection of resistors. So for example, if we have these connections of resistors like this, so if we want to find the total resistance for this connection for resistors, we cannot apply directly the formula that we have for series, parallel, or series to parallel connections for resistors. Because, as we can see, these resistors are neither connected in series, parallel, nor series to parallel connections, right? So actually, we can apply delta and Y connection for these resistors. So what do we mean by delta and Y connection of resistors? So from the word itself, for delta, it means that we have the symbol delta or a triangle. So it means we have resistors connected in this form or in a triangle, 3 resistors. And then these 3 nodes of resistors are somewhere connected in another part of the circuit. Okay? How about for Y? So likewise, the connection of resistors resembles the letter Y. So for example, these 3 resistors are connected in Y connections because it resembles the letter Y, right? So again, these 3 terminals of this Y network of resistors can be connected to any other part of the circuit. Okay? So if we see at first that a connection of resistors involve delta or Y, we can actually transform them from delta to Y or Y to delta by using a formula. So let's discuss the formula in converting a delta to Y network of resistors or Y to delta network of resistors. Okay, so we have here delta connection of resistors that involves RA, RB, and RC. And superimposed with this delta connection of resistors are the corresponding Y connections of resistors that involves R1, R2, and R3. And then we assume that this delta and Y connection of resistors are connected to the nodes A, B, and C so that they can be connected via wires to any other part of the circuit. Okay? So in converting a delta to Y or Y to delta network of resistors, it is important for us to take note of the nodes where they are connected. As in this figure, they are connected in nodes A, B, and C, right? Okay, so given here the formula to convert a Y to delta and delta to Y network of resistors. So let's start with Y to delta. So let's say we are given originally a Y network of resistors. In this figure, we have resistors R1, R2, and R3. We can convert the value of the corresponding delta network of resistors RA, RB, and RC using this formula. So for every numerator of each of the delta resistors, they will be the same. This is the sum of the products of each of the Y resistors taken 2 at a time. So all of the numerators are the same here. Okay? And for the denominator, it will be the Y resistor that is opposite to the converted delta resistors. So for example, in this figure, opposite of the RA is obviously R1, right? So that's why it will be in the denominator for the value of RA. Applying the same concept for other resistor, let's say RB, the numerator still the same, R1, R2 plus R1, R3 plus R2, R3 over this time, the Y resistor opposite to the resistor RB in the figure. So obviously, opposite the resistor RB is what? R2, right? So that's why it has a denominator of R2. And lastly, for RC, we have R1, R2 plus R1, R3 plus R2, R3 over R3. R3 is the opposite Y resistor for resistor RC in the figure. Okay? So that's the pattern for Y to delta formula. How about the pattern for delta to Y network of resistors? So this time, originally, we are given delta resistors with RA, RB, and RC. Now, to convert each resistor to the corresponding Y network, for R1, the formula is equal to RB times RC over RA plus RB plus RC. So this time, in delta to Y formula, all the denominators of each converted Y resistors will be the same, which is equivalent to the sum of the resistances of each of the delta resistors. So RA plus RB plus RC. How about for the numerator? So there is also a pattern. So if we consider R1, we will have the numerator for R1 as the product of the two adjacent delta resistors to that. So what are the two adjacent delta resistors to R1? So this is R1, right? Obviously, the two adjacent are RB and RC, right? Because they are close to R1. So therefore, the numerator of R1 will be the product of the two adjacent resistors. So RB times RC over the sum of the resistances. Applying the same concept for R2, this time, what are the two resistors adjacent to R2? So this is R2. The two adjacent resistors are obviously RA and RC, right? So for the numerator of R2, it will be the product of RA and RC over the sum of the resistors. Likewise, for R3, the adjacent to R3 are what? RB and RA. So that's why the numerator is RA times RB over the sum of the resistors. Okay, so just remember this formula for transforming Y to delta or delta to Y network of resistors. Okay? Now, we have special case. That is, if all the delta resistors are equivalent to a single value, let's say R delta, as well as all the Y resistors are equal to a single value, let's say Ry. So, when we convert the Y to delta, a single delta resistor will be equal to 3Ry. So, it will be the same for all the 3 delta resistors. It will be 3Ry. Likewise, for delta to Y, the Y resistors, Ry, will have a single value, all of the 3, that is equal to R delta over 3. Okay? So, to illustrate the concepts and formula for converting a delta to Y or Y to delta network of resistors, let's solve some examples. For the first problem, we have find the equivalent resistance R sub T of the resistors connected below. Given network of resistors R1 to R5, that has a single value, right? 3 ohms. And then we need to find the total resistance R sub T across terminals A and B. So we actually have a Y and delta connection of resistors here, right? So the resistors connections are drawn in square shape, right? But we can actually redraw this network of resistors in triangle shape so that we can visualize better the delta and Y connection. So if we try to redraw that, it can be drawn like this. Right, so this is R1, R2, R3, R4, and R5. And these are the terminals A and B, where we will find the total resistance. So it is easier for us to visualize the delta and Y. So we have one delta and another delta here, right? So we also have a Y here and another Y here, right? So the goal here for this connection of resistors is to have a conversion from delta to Y or Y to delta network of resistors, so that after that, we will have an equivalent connection of resistors wherein we can now apply the series to parallel connection of resistors. Okay? So it's up to us to decide if we want to convert delta to Y or Y to delta and what part of the circuit we will convert. Okay? So let's say I want to convert this Y resistors into delta. Okay, so if we try to do that, let's consider the nodes. So for the given circuit, the Y that I will consider are connected to the nodes, let's say node A, node B, and this node C. So therefore, the corresponding delta network should also be connected to the 3 nodes. So I will draw the corresponding delta network. Okay? So let's say this is RA, RB, and RC. So since all the resistors in the Y network are all equivalent to a single value which is 3 ohms, we can apply the special case formula for delta to Y conversion. What is that? So the R delta resistor is equivalent to 3 Ry, right? So that each of our delta resistors RA, RB, and RC are all equivalent to 3 times the single Y resistor, which is all equivalent to 3 ohms, right? So therefore, RA is 3 times 3. Likewise, for RB, it's 3 times 3. And for RC, it's 3 times 3. All equal to 9 ohms, right? So if we try to redraw the converted circuit now, we can delete already this Y network because we have replaced them by these delta resistors. So we now have RA as 9 ohms, we have RB also as 9 ohms, and we have RC also as 9 ohms. So what is now the circuit that we have? So if we try to redraw, so we now have this RA, which is 9 ohms, and we have this R2, which is 3 ohms, and we have this RB, which is also 9 ohms. We have this RC, which is 9 ohms, and then R5 equals 3 ohms. Okay, and this is node A, node B, node C, and this is where we will find RT. Okay, so as we can see, we have now reduced the connections as what? So this is parallel, and these two pairs of parallel resistors are in series. So if we redraw that, it will be like this, right? So this is 9 ohm, this is RB, 9 ohms, right? This is R2, 3 ohms, this is R5, 3 ohms, and this is RC, 9 ohms. Okay? So that we can find the total resistance RT as what? So simplify this first. Parallel resistors, right? So what is the formula? 1 all over sum of the reciprocals, right? So this resistors is equivalent to this value. So what is that value using calculator? So this is actually equal to 9 over 4 ohms. So this pair of resistors have also equivalent value of 9 over 4 ohms, right? Because they have the same value of 9 and 3 ohms. So that we now have this 9 ohm resistor parallel to the two series 9 over 4 ohm resistors, right? So we can combine these two series resistors as what? Just add them, right? So 9 over 4 plus 9 over 4 is what? 9 over 2 ohms. So that we can redraw again the resistors as 9 ohm parallel to 9 over 2 ohms. So this is again RT. So that the final value of RT, since these two resistors are in parallel, applying again the formula for parallel resistors, it is equivalent to 1 all over sum of the reciprocals, right? So 1 over 9 plus 1 all over 9 over 2. So therefore, what is the equivalent resistance RT? RT is equivalent to 3 ohms. So therefore, the total resistance of the network is 3 ohms. Okay? Next we have, find the total current I sub T for the given circuit. Okay, so this time we already have a circuit wherein we have a DC voltage source equal to 25 volts, and across this DC voltage source, there is a network of resistors connected as shown, right? So we need to find the total current IT that will flow through the circuit. So we can find the total current IT if we have found the equivalent total resistance for the circuit, right? By using Ohm's law. That is, we will have IT is equal to VT over RT. So VT is 25 volts. So therefore, we need to find first the total resistance RT. So as we can see from the resistor network, we can apply the delta to Y or Y to delta transformation formula in order for us to find the total resistance, since we involve here delta and Y, such as this upper delta, this lower delta, this Y, and also this Y. So it's up to us to decide what to choose to transform. So let's say I want to transform this upper delta into Y. Okay? So I will consider first the nodes where this delta are connected. So obviously, one of the connections is this node, let's name it as A. And then other connection is this node, let's name it as B. And lastly, this node, let's name it as C. So therefore, in these three nodes also, we will connect the equivalent Y network of resistors. So therefore, if I draw the Y network, it will look like this. Okay? And I will try to name it as R1, R2, and R3. Okay? Now, we will apply the formula for transformation of delta to Y as what we've discussed above, right? So, let's find first R1. So, the formula, if we can remember, so for the numerator, it is the product of the two resistors adjacent to R1. So, in the delta, what are the two resistors adjacent to R1? So, this is R1, right? So, the two adjacent resistors are 10 and 20 ohms. So, we will multiply them in the numerator. So, 10 times 20 over. So, what is the constant denominator for the Y to delta formula? The sum of the delta resistors, right? So, we will add 10, 20, and 50. So, we have 10 plus 20 plus 50. So, what is the value of R1 using calculator? So, it is equal to 2.5 ohms. Okay? Now, for R2, this time, what are the two resistors adjacent to R2? This is R2, right? So, what are the adjacent resistors? 10 ohms and 50 ohms. So, therefore, the numerator will be 10 times 50 over the sum. So, 10 plus 20 plus 50. So, using calculator, it is equal to what? 6.25 ohms. Lastly, for R3, this time, what are the two adjacent resistors to R3? So, this is R3. The adjacent resistors are 20 ohm and 50 ohms. So, therefore, we have 20 times 50 over 10 plus 20 plus 50. So, it is equal to 12.5 ohms. Okay? Now, we can already delete this delta resistors being replaced by the Y resistors, right? So, this will be now the new circuit. So, we will write now the value. R1 is 2.5. R2 is 6.25. So, R2 is 6.25 ohms. How about R3? 12.5 ohms. So, R3 is 12.5 ohms. Okay? Now, looking at the new circuit, we can combine resistors, right? So, this R2 is in series with 25 ohms. And this R3 is in series with 30 ohms. And likewise, these two pairs of series resistors are in parallel. Okay? So, we can combine them as a single resistor. So, let's start with R2 being series with 25 ohms. So, if the resistors are in series, the combined resistance is just the sum, right? So, we have 6.25 plus 25 is what? 31.25 ohms. So, I will delete and replace it by a single resistor equivalent to 31.25 ohms. Likewise, for R3 and 30 ohms, so we can combine them by adding the resistance. So, 12.5 plus 30 is what? 42.5 ohms. So, replacing by a single resistor equivalent to 42.5 ohms. Okay? Now, these two resistors are in parallel, so we can apply the formula for combining two parallel resistors as what? So, 1 over the sum of the reciprocals, right? So, 1 over 31.25 ohms plus 1 over 42.5 ohms. So, how many is that? Approximately 18 ohms. Okay, so I will replace these two parallel resistors as a single resistor equivalent to 18 ohms. Okay, next, we can see that R1 is in series with 18 ohms. So again, we can combine them by adding the resistance. So 2.5 plus 18 is 20.5 ohms. So replacing with a single resistor that has a value of 20.5 ohms. Lastly, we are left with two parallel resistors, 20.5 and 15 ohms. So we can combine them using the same formula as this, right? So we have 1 over 20.5 plus 1 over 15. So how many is that? So approximately 8.66 ohms. So that we can replace the two parallel resistors as a single resistor equivalent to 8.66. Okay, so we have 8.66 ohms. So this will be now the RT, right? So we can now find the total current IT using Ohm's law. So IT is equal to VT over RT, right? So VT is 25 volts. So we have 25 volts divided by RT, which is this, 8.66 ohms. So using calculator, what is the value of IT? So it's approximately 2.89 amps. So therefore, the total current flowing through the circuit is 2.89 amps. Okay? Okay, so I think that's it for this video, Delta and Y connected resistors. So I hope you learned something from this video and thank you for watching.